I welcome you all for this session on analysis of indeterminate structures using slope deflection method. Now, in this session, we will be discussing on how to apply a slope deflection method to calculate a simple indeterminate beam. In the one of the previous session, we had taken a prop cantilever beam, and we had analyzed that with the help of displacement compatibility condition. Now in this session we will see how to apply slope deflection method to calculate the internal forces and also the reactions. We will be drawing the shear force diagram, bending moment diagram, and the elastic curve. Now we have taken a simple example. We are required to analyze this indeterminate beam by slope deflection method, wherein we can see that one end is the joint A is fixed and joint B is a roller support or a pin support. It is subjected to a uniformly distributed load of W kilonewton per meter over a span of L, and the flexural rigidity EI is constant throughout the length of the beam. And looking at the beam, we can say that the rotation at A is equal to 0 since it is fixed at joint A. All the rotations and translations are constrained, so we can directly say that theta A, the rotation at A, is equal to 0. And the next step is that we are required to calculate what are the fixed end moments. That is, if both joint A and B are fixed, what would be the reaction which gets generated at joint A and joint B? We know that for a span of L, for a uniformly distributed load, MFEB works out to be minus WL square by 12 because it is in anti-clockwise direction, and MFBA is equal to plus WL square by 12. Now we'll apply a slope deflection equation. Basically, slope deflection equation in EB is equal to moment at A for span EB is equal to MFAB, that is fixed end moments at A for span AB, plus 2EI by L into 2 into theta A plus theta B minus 3 delta by L, where theta is the rotation at A and theta B is the rotation at B, and delta is sinking of support or settlement of support. In this present case, we have not considered any of such things, so I can say delta is equal to 0. And because of the boundary condition, I can directly take value of theta A is also equal to 0. I can simplify and write this equation as minus WL square by 12 plus 2EI theta B by L. So I will call this equation as 1, and I will apply the slope deflection equation at joint B as well for span AB. I can write an equation MBA is equal to MFBA plus 2EI by L into 2 theta B plus theta A minus 3 delta by L. Similarly, here also I will take delta is equal to 0 and theta A is equal to 0 by virtue of boundary condition, and I will substitute what is the fixed end moment at B, that is MFBA is equal to plus WL square by 12 plus, in simplification we will get it as 4 EI theta B by L. So now we have two equations, one is MAB and what MBA. These are the joint moments. MAB is acting at joint A and MBA is acting at joint B. We have these two moments which needs to be calculated, but we have one unknown in these two equations are theta B. Theta B needs to be substituted, or theta B needs to be calculated by solving these two simultaneous equations. Now what we'll do is, from this I will going to apply a joint equilibrium condition. Now in order to calculate theta B, we know that at joint B is a hinged support. At this support, it is allowed to rotate. The beam is allowed to rotate, and if I draw the bending moment diagram, the bending moment at B has to be equal to 0 since it is allowed to rotate. Now I will make use of this joint equilibrium condition, and I will say moment at B, which is MBA, is equal to 0. And from equation 2, we have an equation for MBA, which is WL square by 12 plus 4EI theta B by L. I will equate it to 0. Once I equate it to 0, I have only one unknown in this equation. I will be able to represent theta B in terms of load, span, and the flexural rigidity. So theta B would going to be equal to minus WL square by 12 into 4 EI into L, so which works out to be minus WL by 48 EI in terms of radians. Now, as in the equation, I will substitute EI into theta B as a component. So I will calculate what is EI theta B, which works out to be equal to minus WL by 48. So I'll use this, substitute this EI theta B in equation both 1 and 2. That is, from if I substitute this in equation 1, I'll be getting what is the bending moment at A, which is MAB. So substituting that in equation 1, I'll be getting the bending moment at A is equal to minus WL square by 8. So the negative sign indicates that it is a Hawking bending moment. It's a negative bending moment. And by virtue that of joint equilibrium condition, that MBA has to be equal to 0 since it is a hinged support. Now, once I get this bending moment, I should be in a position to calculate its reaction so that I also write the shear force diagram as well. Now, what I'll do is I will let us rewrite this beam, prop cantilever beam, by releasing the moment. What I'll do is I'll just rewrite it as a simply supported beam, and at joint A, I'll apply a moment MAB which I have calculated. Anyhow, moment at B is equal to 0. Now, and joint A is a pinned support. Since there are no horizontal forces acting on the beam, so horizontal reaction we can ignore. We will have only vertical reaction at A. I will call it as VA, and the vertical reaction at B, I will call it as VB. Now, by applying the equations of equilibrium, basic equations of equilibrium, I'll apply summation of moment about B equal to 0. If I take moment about B equal to 0, VB doesn't cause any moment as it is passing through the moment center. This MAB, BA, and this uniformly distributed load needs to be considered to calculate moment about B. And this VA is creating a clockwise moment, so I'll take it as positive VA into L minus this MAB is acting in the anti-clockwise direction, so I'll take it as minus MAB. And this uniformly distributed load is creating a moment in the anti-clockwise direction. This load is trying to create a moment in this direction. So this also I'll be taking it as negative minus WL square by 2. W into L, which is acting at a distance of centroidal distance of L by 2. So which works out to be WL square by 2 is equal to 0. So from this equation, the only unknown which I have is VA. So by substituting what is MAB, which is already been calculated in the previous slide, which is equal to minus WL square by 8, I can substitute. I will be in a position to calculate what is VA is equal to 5WL by 8. I can say it as kilo Newton, and summation, again I will apply another equation of equilibrium, which is summation of vertical force equal to 0. I'll take summation of vertical upward reaction VA plus VB should be equal to the downward load, which is W into N. So with which I already have what is VA and the total downward load. I will be in a position to calculate what is VB, which is 3 into WL by 8. So now we have calculated the reaction with which I will be in a position to draw the shear force diagram as well. Now we have written this beam. Now I will, if in order to write the bending moment diagram, again I will go with the help of a method of superposition, principle of superposition. I will analyze the beam, same beam, for the negative moment which is acting at A separately, and I will draw the bending moment diagram for the uniformly distributed load for the same beam separately, and I will going to superimpose so that I can get the net bending moment diagram. So this is the bending moment diagram moment which is we are writing because of the end moments which we have calculated, and this bending moment is because of the uniformly distributed load which is acting, which I can say it is a simple bending moment, because as I have taken out this moment and I have made the beam into a simply supported beam, I can call this bending moment as a simple bending moment and this as an end bending moment. Now we have a sign convention wherein I can write a sign convention that whatever negative bending moments for the left of the beam, I'll be plotting it above my reference line, and if it is positive, I'll plot it below the reference line, and the reverse of that for the right hand side as discussed in the previous session. So I'll use that. So since we have a negative value, MAB is minus WL square by 8. So I'll plot it above the reference line, and MDA is equal to 0. It becomes 0. So I'll join that with a linearly varying line, and this becomes a negative bending moment. This if you can see that this MAB is trying to fog the beam, and it is creating negative bending moment. Whereas this uniformly distributed beam or a simple bending moment, we know that the bending moment would going to be a parabola and will have a maximum bending moment of WL square by 8 at the midspan. Now I'll going to superimpose the simple bending moment as well as the end moment, so that I will get the net bending moment like this. We'll have a bending moment which is WL square by 8 at the support, and over which we'll have a superimposed simple bending moment with a maximum of WL square by 8 at the midspan. Now this portion is a negative bending moment, and this portion will have a positive bending moment. And this is the portion where the both negative and positive have got nullified. So we need to calculate what is the net effective bending moment. Is that we need to calculate the difference of these two, so that we will be getting what is maximum bending moment. Similarly, I can plot what is the shear force. Shear force is we know what is the reaction at A is 5WL by 8, which goes up, minus the downward forces, which is minus WL, which comes again minus 3WL by 8, and the reaction B is 3WL by 8, plus that it goes to 0. So whatever it is above the reference line becomes positive, and this becomes negative. So this is how we can calculate, we can solve an indeterminate beam with the help of a slope deflection method. So now let us again recollect the steps which we have done. The first and foremost thing is, based on the boundary condition, we list out what are the rotations which are equal to 0 and which are not equal to 0. We'll calculate the fixed end moments. Once we calculate the fixed end moments, we will going to develop slope deflection equation for all the members. That is, we'll be calculating MEB, MDA. If I have multiple span, I'll be calculating the moment at all the joints as well. Once I calculate the slope deflection equation, we are required to develop additional equation by applying joint equilibrium condition. At each joint, the summation of moment should be equal to 0, or if it is an exterior support, if it is a simple support, then the bending moment at that joint should be equal to 0. Based on that, we will develop additional equation with which we will be in a position to calculate the unknown rotation values. Once the unknown rotation values are calculated, we can substitute back in the slope deflection equation to calculate the bending moments. Once the bending moments, the end moments are calculated, we will going to write the bending moment diagram by with the help of superposition. That is, we will draw the end moment, and over which we will going to superimpose a simple bending moment for all the spans to get the net bending moment diagram. And to calculate the shear force, we will be using the same techniques how we have discussed in the previous slide. Okay. Thank you. In the next session, we will take up a problem which will have more than one span and different types of loading, and we will try to apply the slope deflection method to get the bending moment diagram, shear force diagram, and elastic curve. Thank you.